Welcome back. In this video, we'll be solving the problem at the very end of the second derivative test notes. So we want to identify all the local extrema of this function using the second derivative test. If you haven't already tried this problem, I highly encourage you to do so before you watch the rest of this video. Alright, so this problem is going to go through the same steps as the example before it. So the first thing we want to do is find the critical values of this function. So we need the critical values, and this is exactly how we would have started the question if we were using the first derivative test to answer the exact same problem. So we'll take the derivative and find where it's 0. Alright, so the derivative of this function is 15x to the fourth minus 15x squared. Okay. We should always consider where this derivative doesn't exist because it's a polynomial. We don't have that issue, but I want to remind you that every once in a while that does pop up. Alright, so we just need to set it equal to 0 and solve, and those will be all of our critical values. So I have 15x to the fourth minus 15x squared equals 0. I'm going to factor out a 15x squared, so I get x squared minus 1 left over. And then that x squared minus 1 factors into x plus 1, x minus 1. So I can see that my critical values are 0, -1, and +1. Okay, so if we were doing this with the first derivative test, we would put those guys on a number line and start testing derivatives, but we're doing the second derivative test. So now what we want to do is plug our critical values into the second derivative. Exactly the critical values are going to go in. We're not doing test points and intervals anymore. Okay, so I need to take the derivative of my derivative to get the second derivative. So even though I have the factored form of my derivative, I'm going to go back to the unfactored form because this is the easiest one to take the derivative of. So I'll get 4 times 15, which is 60. I guess I should have known that. We'll have 60x cubed minus 30x. That's my second derivative because it's the derivative of the derivative. Okay, so I want to plug my 3 critical values in there and decide what is going on. Alright, so if I plug in 0, I actually get 0 out. This actually doesn't fit into the second derivative test, right? Our second derivative test said, you have a max and min, whether this comes out positive or negative, but if it comes out exactly 0, our test is inconclusive. So what we have is that the function is potentially changing concavity, or at least doesn't have concavity at this spot. So we don't know that it's a max or min. And if you remember, we actually did this problem exactly in the first derivative test section. And what we got was that 0 was not a max or min point because the first derivative didn't change sign. But here we'll just say inconclusive. Okay, the other two should come out a little more normal. So I'll plug in -1. I get 60 times -1 cubed minus 30 times -1. That's -60 plus 30 is -30. Alright, so that tells me that my second derivative is negative. So I am concave down. By I mean F. F is concave down at this critical point. So if it's concave down, I must have a max at -1. And then finally, I'll plug in +1 to the second derivative. That gives me 60 minus 30 is 30. That's positive. So a positive second derivative tells me it's concave up. So I have a minimum at 1. All right. So if we want to answer this with the full xy points instead of just the x values, we would then go back and plug in 1 and -1 to the original function. So I have a local max at -1 comma whatever its y value is, a local min at +1 comma whatever its y value is. And if I plug each of those back into the original function x, I would get a 2 here and a -2 here. And these are exactly the same answers we got doing this with the first derivative test.